Swayam Prabha. Digital India. Educated India.
Welcome back. We got a new topic for you, conformational isomers. What are they? Well, we talked about sigma bonds and pi bonds, and how these are made by taking hybrid orbitals and coming together. So if you have two carbon-carbon sigma bonds coming together, they can make a bond here, right? And they lose about 90 kilocalories per mole. That's a lot. So they're very stable bonds. That means when you say sigma bond and I'm showing you these sticks, they're not really sticks. They're more like electron clouds in between. So this is like an electron cloud in between. So the electron cloud is just what it is, an electron cloud. There's nothing solid here. It's just an attraction between the electrons and the nucleus and the electrons and this nucleus that keeps them together. So the electron cloud can be rotated. So, and it also has a sigma plane of symmetry. It can be rotated in all directions, okay? So this is just an electron cloud in the middle, and you can rotate it. Not so with pi bonds, but sigma bonds can be rotated. Because you can rotate them, there are many, many positions possible for these bonds. They can be close together, they can be away from each other, they can rotate. And these sigma bonds rotate very, very rapidly. Unfortunately, my models don't rotate as much, but it can be like 10 to the 9 times or more per second. So they're very, very fast rotations if you have something like ethane. But if you have lots of other things on it, there might be a barrier to rotation. This is exactly what they mean. So let's say we have a group here. Let's pretend these are CH bonds here, and there are CH bonds. Again, bonds are nothing but electron clouds. So the electron clouds can repel each other. So when you come around like this, there's a barrier here that they have to overcome. So because of that, we have these molecules preferring certain orientations over others. These are called conformation. This is one conformation, this is one conformation. It's the same molecule, different spatial orientations of atoms or groups. So that's pretty much the definition of what conformational isomers are. So it just means molecules with different spatial orientations arising from rotations, I would say rapid rotations along sigma bonds. And those are called conformational isomers. Now, these molecules have different angles between these groups. Those are called dihedral angles, and we'll talk about them. They will have different energies, right? Some are more stable than the others. But the connectivity and the molecular formula doesn't change. And these groups are not bonded to each other. There's no electron sigma bond here or pi bond here. They're just electron clouds pushing electron clouds. Or they can even be like bonds pushing bonds. Those are non-bonded. So the non-bonded interactions between atoms or groups of atoms like methyl, tert-butyl within a molecule. This is nothing to do with intermolecular, between molecules. It's all happening inside the molecule. That's what we are looking at, within a molecule. Creating different dihedral angles, creating different isomers, different spatial or conformers with varying dihedral angles, theta, and energies, but having the same molecular formula and connectivity. these two groups, let's say this is a methyl and this is a methyl, they're on adjacent atoms. These are called vicinal. So when you have vicinal atoms, you can have two types of interactions. So let's say that one is an X and one is a Y. These are vicinal, but they're non-bonded between X and Y interactions. And they can be either in an open chain molecule. You can have two types, steric. And steric is nothing but electron clouds. This is an electron cloud. This is an electron cloud. I kind of put minus on here. I don't know if you can see it. Bumping into each other and repelling each other so that, well, they don't want to meet neighbors, so they shift out of the way. But then these are rotational isomers. So when they come back, there's a barrier. And so this is a high energy form. This is a low energy form. So they alternate between these forms. Those are some of the possible conformations. There will be a lot more. Steric and torsion. So we'll talk about both of them. These are kind of strains on the molecule because they can increase the energy of the molecule and create a barrier. So we call them steric strain and torsional strain. Steric strain, as I said before, is between non-bonded electron clouds repelling each other. Repelling each other. They can be vicinal, and sometimes they can even be 2 carbons away. It will be called 1,3-diaxyl, and we'll talk about it. And causing a barrier to rotation. And we can calculate how much that is. There are lots of computational programs that calculate that. We are going to look at eclipsed, gauche, and 1,3-diaxial. Eclipsed, and when you say eclipse, I'm sure you're thinking solar eclipse and lunar eclipse, and it's something like that. Eclipse means they're one behind the other, right behind each other, or right next to each other. This is eclipse. And then this is going to be anti. So we're going to look at the eclipse. But does that mean that none of these have any kind of interactions? Of course they do. But because we're using computational programs to calculate these energies, we got to set some parameters inside the program, and we don't want a huge data set, so we calculate at 60-degree increments. So that's why we draw these graphs at 60-degree increments. At 60 degrees, so all of this is a very high steric, because electron clouds are repelling each other. This is also high steric. Then you come to a 60, we calculate that. That's called a gauche interaction. So eclipse, we can say 0 degrees. Or gauche, it's 60 degrees. Now when you go greater than that, it kind of falls off. And this is 180. There's nothing here, no steric at all between these two groups. So that would be the most stable conformer. And then we come back again. Again, there'll be a barrier. Again, gauche, and then eclipsed. So these are things that are going to be periodically changing because of the rotation along the sigma bond. And later on, we will talk about 1,3-diaxial. These are the 3 types. This is 1,3-diaxial when you have chair conformations. Let's look at torsion. Torsion is a kind of force. If you have 2 parallel bonds, these are also vicinal. That means they're right next to each other. So for torsion, you've got to be right next door. If you have 2 bonds that are like this, you have an electron cloud here and an electron cloud here, and you're going to repel. This is a CH, let's say, and this is another CH, let's say. They're going to repel. And so when you go to the opposite direction here, this bond also has an anti-bonding orbital. The anti-bonding orbitals in a CH sigma is empty. So the empty bond can kind of help this filled bond relieve some of its electron density in here. So that's like a hyperconjugation. So filled bond releasing into an empty bond. I mean, it's almost like your neighbors left and gave you the key and you can kind of ease in. That doesn't mean you move in. It's not a shift. This empty orbital kind of helps this bond to relieve some of its electron density and be stabilized. So the whole system energy comes down. So because of that, again, opposite anti is favored over parallel. So let me write that down before we forget. The repulsion of parallel and adjacent sigma bonds causes the sigma bond to stabilize with the adjacent sigma star bond. Repulsion between parallel and vicinal bonds. In this case, we're going to talk mainly about sigma bonds causing a staggered orientation which stabilization between the sigma and the sigma star empty of the adjacent of the neighboring bond. This is a type of hyperconjugation. Now later on you'll talk about HOMO, LUMO, and how the field is HOMO and this is LUMO, and you have a stabilization there. But for right now, don't worry about that. Let's look at some examples. I'm going to draw these out just because it's kind of a new concept. So here is your, let's say this is your molecule here, and you have a sigma bond here, sigma CH. This is just nothing but electron density with a little bit of a proton here and some protons here, sigma CH. And here, this bond here has got a sigma star. Every sigma bond has a sigma star bond. And the sigma star bond here is going to help this go over here. That's empty. And this is full. When you say full, it means full of electrons. All right, so here we go. We are going to talk about some examples. Let's talk about just a simple, plain old ethane. Let's talk about ethane. This is a carbon, this is a carbon, 3 hydrogens here. And you can see that this can rotate. So from where you are, it's hard to tell whether these are parallel or whether they are a little bit off. What's the angle? It's hard to test, right? So there's this guy from Ohio State called Newman who said, why do we have to always draw it like this? Why can't we draw it like a head-on view? So now you can see when you look through here, you can see these are exactly parallel. Now they have an angle. This is about 60, 120, 180 between the top and the bottom, right? 270, 300, 360. And again, it's all computational work that set these 60-degree increments. The molecule doesn't go like strut like this. The molecule is just rotating very, very smoothly. But we are calculating 60-degree increments. So let's look at ethane. CH3 is ethane. This is again a molecule that you're going to pay the gas company for heating up your home. A small part of it, maybe like 20-30% of your gases. So here, this is called kind of a sawhorse projection. Again, the angle between this and this is called the dihedral angle. So here, if you take these two, if you keep it like this, you can see the dihedral angle is 0. Now that angle between these two, that's the dihedral angle theta, is 60. So that's what we mean by dihedral angle. It's between this bond and this bond. And it's easier to see in a Newman projection. So let's draw out ethane, and ethane is going to be, let's say, this is the front carbon, let's say, and that's 1 carbon and three hydrogens. And the back here is going to be again 3 carbons and, 3 hydrogens on a carbon. this angle between this hydrogen and hydrogen is called the dihedral angle. Again, it's hard to see what the angle is when you draw it like this. So you have a view from right where you are. This is a dot, and the back carbon we draw as a circle. So let's draw the dot. The dot here has 3 CH3s. So I'm going to draw it out here. This is called the Newman projection. And you'll be drawing these throughout the semester for transition states and stuff like that. So when you look at it, you're going to see this carbon first, head on. So I would say a head-on view. So that is a dot with 3 hydrogens. You don't put carbon here. This Newman projections mainly for organic molecules, so it's assumed that those are carbons. And the back carbon is drawn as a circle. Well, you can draw the circle and then put the front carbon. That might be easier. In this case, it looks like they are kind of parallel, and there's like a 0-degree dihedral angle. So here's this. So this is how you would draw it, because it's impossible to draw exactly parallel here. So this is like a 0-degree dihedral angle, or theta is equal to 0. Now, as I said, we don't draw the 1 degree and the 2 degrees. We just go 60, as I said, because of the computational work. And so here we're keeping the front the same and rotating the back. There is no rule that says you cannot keep the back the same and draw a circular front. Both are correct. Okay, Newman didn't come up with a rule for that. So therefore you can rotate the back. So here 60 degrees. And why is it rotating? Why doesn't it want to be like this? Again, as we said, repulsion between parallel and vicinal sigma bonds, and also that's 1, and 2, causing a stabilization between the sigma and the empty sigma star of this. There's a sigma star that's going to stabilize the CH. So therefore, you are going to have a relief of the torsion. So you're going to go back. The back carbon is going to be like this. That's the one I'm rotating. And the front carbon, I didn't rotate. You cannot rotate both, because then you wouldn't know what the angle was. So you just rotate one 60 degrees. In this case, we have chosen to rotate the back by 60 degrees. So the dihedral angle here is 60. This is 60. If this is 60, then obviously all of these are 60, right? So that's going to be that. Now they have calculated, again, these are computational calculations about how much energy is released when you go from this repulsive interaction to this stabilization interaction. So here the anti-bonding orbital of this CH is stabilizing this CH. And here this is repelling. So the difference in energy between these two states is 4 kilojoules per CH-CH interaction. That means this is 4 kilojoules per mole, obviously. And this is 4 kilojoules, and this is 4 kilojoules. So 3 times 4 kilojoules per mole higher in energy for this form over this form. So here we are only talking about the energy of the non-bonded interaction. So when we say potential, usually they say potential energy. That doesn't mean this is the entire potential energy of the molecule, the molecular bonds and all of these bond energies. The potential energy due to non-bonded, I'm going to put NB, interaction. That's 12 kilojoules higher for this than this. So you are going to start, let's say this is 0, then this is 60. Then if I rotate it again, you're going to go through the same eclipsed. Then it gets staggered. Then eclipsed, staggered, eclipsed, staggered. So this is going to repeat over and over again. So if I, let's say, label this molecule A, and this molecule B, you will see A would be high energy, 12 kg. So this is kilojoules per mole, and this will be 12. And then it'll come, the non-bonded interaction would drop, and then again, when you keep rotating, it's going to go back to A again. So this is A, B. Then you go to another 60, and then another 60, and so on. So 240, 300, 360, and you're going to alternate between these two states. Those are the only two possibilities for that. So it'll go up and down, and up and down, and up. It's just a wave. So you would see that these are going to be a very periodic and repetitive pattern for a molecule like this that's just CH bond ethane. Now if you have other groups here, that's going to be a little different. If you put another group, let's say here, now that's not going to be the same because you have other interactions here. So let's talk about another molecule that has a group. It could be just a methyl group. So let's talk about propane. Propane is the gas in the tank that you're going to take when you go to barbecue. It's another fuel. Most of these alkanes are fuels. So here you are going to have the CH3, then a CH2, then another CH3. Putting this like this just to show you that you have a group here. So let's draw it out. See, it's always a good idea to draw it out like this before you start drawing the Newman. CH, H, two hydrogens here, and then you're going to have this group over here, CH3 group here. So we are going to again do a rotation of, see all of the conformational possibilities for this molecule. Well, you have a lot. This is going to move, this is going to move, these are going to move, a lot of them. Is it possible to draw all of them at once? It's almost impossible. So what we do is we say, okay, just let's do one sigma bond rotation at a time and see what the energies are. This is probably the one that's going to have a lot of variations. So let's draw this. In order to draw this, you have to find the dihedral angle between this and this. So this is probably the best Newman to do that. You can look at this and say, okay, this is 0, this is 60, this is again 120 and 180, 240, 300, 360. You see? So it's easy to now figure out what the angles are. So therefore, we're going to look at it head on between 1 and 2. It's the same if you look between 3 and 2, but we always try to say the lower numbers. Here, it's between 1 and 2. So this is going to be always the front carbon is your dot, and you will have a hydrogen, in 3 different directions. Now these are 109.5. We didn't suddenly squish these hydrogens to 120, but when you look at it head on, you cannot see the difference. You can only see like a Mercedes-Benz symbol, right? So that's 120 degrees. And the back carbon, this is going to be your circle. So that's your circle carbon, the carbon number 2. And then that's got 2 hydrogens and a methyl. So here are the 2 hydrogens, and those are going to be parallel to these, and a methyl that's going to be popping up on the same side of this hydrogen. And I'll just put CH3 there. Now that, what do you think is going to be the state of this molecule? Happy, unhappy, stressed, drained, all of the above, right? We're unhappy and stressed because, well, these need some space, so they get out of the way. So then we rotate the back carbon. Again, there's no rule that you can only rotate the back, but I'm going to just rotate the back. And you you can have the methyl coming to a side, let's say just a 60-degree rotation, and this methyl is going to come to the side. And then all of them are going to go 60, like when you do your steering wheel 60, right? All the spokes go 60. So there you go. And here is your front carbon, that's C1, and that's got 3 hydrogens on it. And the hydrogens are so tiny. There's nothing here. This electron cloud here is not a huge electron cloud like this that we showed before. This is just almost nothing. So the steric here between this electron cloud and this electron cloud is negligible. However, the torsion is considerable. So the torsion is get relieved. But then you go back at another 60, which you have to, again there's torsion, the same amount of torsion, then a relief. Then again, and same amount of torsion here between this CH and this CH3C. Then again a relief, and then again the same torsion again. So you can see it's a repeating pattern just like here. There are only 2 possibilities. It's either all eclipse, 2 CH eclipse and a CH eclipse, or a staggered. So they're going to go alternating, in the same thing. So here this is theta is equal to 0, let's say is C, theta is equal to 60, let's say is D, and we can calculate the energies. So torsion, CH between 2 CH bonds is, we already said, was 4 kilojoules per mole. Torsion between the CC and the CH are different because the C carbon obviously is a lot bigger and the CC bond has more electron density in it. So CHCC is 6 kilojoules per mole. So then now we can calculate the total. So we said this is 4, and this is 6. Again, kilojoules per mole. So this whole thing is going to be 14 kilojoules per mole, higher than this. Again, the steric here is negligible. There's no gauche here. Kilojoules per mole. And you can see like an undulating movement here, 0, 60, 0, 60, and so on. And so that's what we have. And 14 kilojoules. To 0 extra energy, to 14, to 0, to 14, to 0, to 14, and on and on and on throughout infinity. So that's conformational isomers for you. Each one of this is a conformer, but we are only drawing it in 60-degree increments. If you change the angle, you get a different conformer. So these are just different spatial orientations arising from rotations along sigma bonds. Non-bonded interactions between atoms or groups within a molecule, creating different conformers with varying dihedral angles and energies, but having the same connectivity. We never broke a bond or moved a bond or made new bonds. It's the same bonds. Why is this important? Because pharmaceutical industry, when they make a drug, let's say they want to make a drug that mimics a steroid, and they want it to bind in the same place the steroid binds, say prednisone or whatever. Shape is very important because molecules tend to live in this energy minimum most of their lives. They go through this real quickly, but they come in and live here. So you want to make a drug that mimics the energy minima. So this is called the energy minima. That's what you want to make when you make a drug. So then it will mimic that molecule that you're trying to imitate and bind in the same pocket while it's in energy minima. Maybe your energy minima is lying on the sofa and falling asleep. So molecules also have their energy minima. They love to be in that position. The energy maxima is this, too much strain. So to relieve that, they go into the energy minima. One little thing about bond distances is the bond distance between these CHs different when they rotate? Of course, they're going to be different. So here in this eclipse conformation, the CH is 2.29 angstroms between these two. And then when it moves away, obviously it gets a little bit longer, but not too much. It's 2.55 angstroms. So you can see the distance getting bigger would cause less torsion. It would also cause less steric, except with hydrogens the steric is minimal. Over here when you have the CH and CH3, this is going to be 1.9 angstroms. Okay, because carbon's a little bigger, right? CH3 group. And then when it goes over here, this distance, this angle is 60, the distance there is 2.4 angstroms. So you can see as the distance increases, the energy also drops. All right, guys, so see you next time. Bye.